Alright, so the recording has begun. This is day number 1, week 7 of our journey together. And it's such a delight to have each and every one of you here on this occasion. We're going to continue our discussion of probability. The last time we were here, we looked at the probability rule that deals with the union of probabilities, whereby we said that the probability of A or B is going to be equal to the probability of A plus the probability of B. We call that the addition rule when dealing with probability. Today we're going to be looking at the multiplication rule, and we're going to see how far we get with that. Oh, also we also look at a very important sample space, and that sample space is the standard deck. And we looked at that and we observed what happens when we're dealing with the standard deck. We said that the standard deck has 4 suites. That's hearts, diamonds, spades, and clubs. And we said that the standard deck has 13 denominations, which includes 3 picture cards. That would be the kings, the king, the queen, and the jack. It has an ace, and it has number cards, which has numbers on them from 2 to 10. And so that's the standard deck. Notice that the standard deck is also cut in half in terms of its colors. So when we look at the standard deck, we know that it has 26 red cards and it has 26 black cards. And so it's cut half and half. And the standard deck is one of those sample spaces that we use a lot in probability. So probability questions can involve the standard deck as well. So besides the standard deck, we also look at... Hello? Hello, can you hear me?
Yes, I already received the open Zoom meeting. I can't see nothing except the light bulb.
You can't see my screen?
We can hear you, but we only can see the open Zoom meeting. We can see what you're reading.
No, I'm not reading anything. Sorry.
Oh.
No, I'm just providing an overview of what we did last class. Sorry. Alright, I guess y'all want to see. Alright, probably want to see the... Okay, no problem. I just given an overview, sorry. Alright. Okay. Okay. Alright. Yeah, so the standard deck is one of those sample spaces that we use when we're looking at probability. And that's not the only sample space that we look at. We look at also the sample space that is the dice, right? We also look at and the dice has 6 sides. So 1, 2, 3, 4, 5, and 6 is the sample space for the dice. We also look at for the coins, all right? And when we look at the coin, the sample space for the coin would be heads and tails. And we looked at probability questions concerning dealing with rather the coin. Today we're going to continue with probability, but like I said, we're going to be looking at the multiplication rule. So I want you to head up for me. Today is Monday, the 15th of August. So find something to write with and something to write on. Remember that after class, I want you to send me the class notes. All right. So today is Monday, the 15th of August, 2022. The subject is indeed mathematics. The topic we're going to be looking at is the multiplication rule. The multiplication rule for probability. the multiplication rule for probability. That is what we will be looking at today. The multiplication rule for probability. So the multiplication rule states the following. So let's get a box, and okay, this is the problem. Okay. Let's make sure our shade that no fill or blue, and then you're gonna make this increase here. Okay, good. So let's increase that. So we're looking at the multiplication rule. So in this box, I'm going to be placing the multiplication rule. Right, so the multiplication rule. All right, so the multiplication rule states the following. It says if A, so capital A, so let me extend this outward. So the multiplication rule says if A and B are independent events, which means that when we say they're independent events, which means that the probability of one thing happening does not affect the probability of the other thing happening. So that is to say, they do not affect each other. Then the multiplication rule states that. So let me get another text box. Then what that means is that probability, so that's the probability of A and B is going to be equal to okay, one moment. The probability of A and B is going to be equal to the probability of A times B. One moment. Okay. Oh wow. Oh wow, I just lost it. Okay, so I have to start over because it just, deleted itself, interestingly enough. So give me one moment, let me write it again. One moment, let me write it again because apparently it just decided to delete itself. So forgive me for that. The topic is multiplication rule for probability. So again, if A and B are independent events, which means that they do not affect each other, then the rule states the following. That the probability of A and B is going to be equal to the probability of A multiplied by the probability of B. Right? So this is the multiplication rule. Remember, for the addition rule, if it was probability of A or B, what would we have done, Sierra, for the addition rule? If it was probability of A or B, what would we do? Remember, for the addition rule, Sierra?
I don't remember.
Wouldn't we add them? Wouldn't we add the probabilities?
Oh yeah, so it'll be PAB.
Exactly. So it'll be the probability of A plus the probability of B if it was the addition rule. But for the multiplication rule, it's different. We multiply the probabilities. All right. So be careful. Addition rule, when it's or, so if it's probability of A or B, we add the probabilities. So let me show you what I mean. So if we have the probability of A or B, sorry, let me clear that. So if we have the probability of A or B, then we know that's going to be equal to the probability of A plus the probability of B. That is what we call the addition rule. That's what we did last week. But for the multiplication rule, if you have the probability of A and B, all right, then it's going to be equal to the probability of A multiplied by the probability of B. All right, so that's how we would do it. So for the addition rule, sorry, let me close this in. So for the addition rule, we add the probabilities. For the multiplication rule, we multiply the probabilities. And by the way, the probability of A and B is the same thing as the probability of A intersect B. So this is really the intersection. And the probability of A or B is the same thing as the probability of the union of A and B. That's another way to write it. Okay. So let me make a note of that in the definition. So this can be said the same way as if we were to look at the union. So the probability of A not union, intersection. So the probability of A intersect B is P P times P, sorry, is the probability of A times the probability of B. So did they put it in? No. Let's do it again. Insert. Good. All right, so those are the two ways to write the multiplication rule. Again, the multiplication rule states that if we have, if we have two independent events, A and B, and we're trying to figure out what's the probability of A and B. Now, when we say independent events, that means that the probability of one does not affect the probability of the other. All right? If we're trying to find the probability of A and B, it's going to be probability of A times the probability of B. All right? So that's the multiplication rule. So let's look at an example of this, okay, to really, cement it for us. So as an example. So our first example is going to be, let's say we have a bag, all right? A bag contains 6 blue balls and 4 red balls. So we have a bag and it contains 6 blue balls and 4 red balls inside this bag. Now, a ball is taken out at random and replaced. Then a second ball is taken out at random. So the first question is, what is the probability that both balls are red? So again, let me explain to you what the experiment actually is, so you can actually have an idea of what's happening. So we have a bag, all right? Sorry, let me erase this so you can actually see what's happening properly. So we have a bag, clear drawings. We have a bag. Inside this bag, we have 6 blue balls and 4 red balls. So let's draw 6 blue balls. So 1, 2, 3, 4. Well, let's do it properly because they don't have to be all in the same location. So it's a bag, so they are randomly in this space. So we have 1 here, 2, 3, 4, 5, and 6. And how many red balls do we have, Deja, inside this bag?
4.
4 red balls. Okay, so this is going to be 1, 2, 3, and 4. So the experiment is, right, the following. What we're going to do is we're going to take, at random, we're going to close our eyes and take a ball from this bag. So let's say we take a blue ball out the bag. Now, once we take the blue ball out the bag, the experiment is we take the blue ball out the bag. So a ball is taken. So we take one ball and then we put it back. All right. And then we take a second ball. Okay. So in total, we would have essentially 2 balls being taken out. Okay. 2 balls are taken out from this bag for each outcome. All right. So that's interesting. 2 balls are going to be taken out for each outcome. So we could take out one ball, put it back, and then take out another ball. So we could take out a blue ball, then put it back, and then take out a red one. And right, and that's one experiment. So the experiment itself is taking a blue ball, taking a ball out of the basket and then put it back, and then taking out another one. So many things could happen, right? One of the things that could happen is we can first start off by taking out a blue ball, right? So we take out a blue ball and then we put it back, and then when we gotta take out the next one, we could take out a red. So that's one outcome. We could take out a blue one first, and then we could take out a red one second. That's an outcome. Another outcome is that we can another thing that could happen is that we can take out a red first, put it back, and then take out a blue. So we can have a red first, then a blue, right? Whatever happens, we take another ball and put it back and take another ball again. That's the outcome. That's the experiment. So let me leave that as such. So they want that we want the probability that both balls are red. Okay, that's what we want. The probability that both balls are red. So let's do this the right way. So the event A, all right, so the event A is going to be that what? The first, so if both balls are red, right? If both balls that be taken out are going to be red, Sierra, what color must the first ball be?
If we taking the 2 reds?
Yeah, and then
Blue?
Both balls
Red.
are exactly, right? So the first one have to be red. And Deja, what must the second one be?
Red.
Red as well. So second ball is red, and first ball is red. All right, so both balls are red. That is the probability that they want us to define, the probability that both balls that we take are red. In order for that to happen, the first event, which is the first ball is red, that event must be true. The first ball we take must be red, and the second ball we take must be red. So in effect, what we are basically doing, we're trying to find a probability of A and B, because we're basically trying to find a probability that the first ball is red and the second ball is red. So the probability of both balls are red equals, the probability that both balls are red equals the probability that the first ball is red plus the probability that the second ball is red. All right, so that's basically what we have. I don't know why this. Give me one moment. Let me clear this. Let me clear this drawing. All right, so this is interesting to me. I don't know why. Maybe I should increase the noise.
I have a question. Why did you put plus? I thought we were multiplying.
Yeah, multiply. Thank you. Because it's both ball is red, so it's gonna be multiplied. Thank you.
I have another question.
Uh-huh.
So would it be wrong if before we even did this, like we went in a sample space? I was thinking in my head you were gonna be like the first outcome could have been red, 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 blue, 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 and blue, red. But I guess not.
That's why I avoided making the sample space. See, the sample space for this experiment is if we could actually do it. I don't think we should do the sample space for this experiment. Because if we do it, the sample space for this experiment actually has 100 outcomes in it. And so we don't want to do that. Because if you think about it, right? And that's why we're using the multiplication rule because what it does for us, right? It separates this, what should I say? It separates this big problem into two smaller ones that are actually easier to find. So let me show you what I mean. So we want the probability that both balls are red. What does that mean? That means that the probability that if we're trying to find the probability that both balls are red, that means the probability of we have to first find the probability that the first ball is red and multiply that by the probability that the second ball is red. Okay, so essentially what we're doing is trying to find the probability of A, because A is the first ball is red, multiply that by the probability of B. Now, what is the probability that the first ball is red? Now, obviously that's going to be a fraction. So let's look at it. Insert. Okay. Caitlin, what's the probability that the first ball is red? That's Caitlin. Caitlin, are you here?
4/10.
4/10. Okay, how did you get 4/10?
There are 4 red balls, and in total, there are 10 balls.
Very good. Where's your sister? Where's Sienna?
Her phone went dead.
Oh, okay, okay. So is she follow along with you or?
Yeah.
Okay. So 4/10. Good. That's the probability that the first ball is red. Makes sense because in total, okay. In total there are 4 red balls, and there are 10 balls in there are 10 balls in the whole entire basket. All right, so 4 over 10. All right, now Jasmine, what's going to be a probability that the second ball is red? Jasmine, are you here? Okay, I'm not hearing from Jasmine. Miss Johnson, are you here? Taisha Johnson, are you here?
Yes, sir.
Okay, good. What's the probability that the second ball is red?
6 out of 10.
6 out of 10? Why you say 6 out of 10?
Because then it would amount to the total amount of balls.
No. Okay. How much red balls are in the basket on the second dime? How much red balls are in the basket?
4.
4. Why is there 4? Isn't it 3? Or it's 4. Why you say 4?
My mistake, 3.
No, you actually right. It is 4. But why 4? Why not 3?
Because there's 4 red balls.
No, more than that. Remember, if we look at the experiment is that when we take a ball from this, we put it back. You understand? So for the first ball, for the probability of the first ball, we took out our first ball was red. You understand that? So we took that out. But then the experiment says that we must put that same ball back in. So when we took out the first ball, it was 3 red balls inside the bag. But we are going to put the one that we took out, we're going to put it back in. So it's still 4 red balls back again. You understand that? Or you want me to explain it again?
I understand.
Okay. So she's right. It is 4 over 10 again. Go ahead, Deja. You was going to say something?
That was Jasmine. I couldn't hear at first.
Okay. Yeah, it is 4. Very good.
I think it's 4.
It is 4. So anyone have any questions with why it's 4 over 10 again? Or you understand? So let me explain it again for good measure.
So it's 4 to 10 because there's 4 red balls and 12 plus 6 is 10.
So it's 4 over 10 because it's 4 red balls. Because look, we have 1, 2, 3, 4 red balls in there, right? So, and how much blue balls? 1, 2, 3, 4, 5, and 6. Remember what the experiment said. The experiment said that we take out the first, remember, for our event, the first ball is red. So we're going to take that out. Okay, so that's our red ball out here. Okay, now when we take it out, right, we have 3 left. But remember, after we take it out, we put it back again. Okay, so when we go on to take the second red ball, it's still 4 red balls that we could choose from. So that's why it's 4 over 10 and 4 over 10. Okay, so the probability of the first ball, red ball, is, sorry, the probability that the first ball is red is 4 over 10, and the probability that the second ball is red is 4 over 10. And remember now, excuse me, we are multiplying.
So you saying that you take out the red ball and you put it back in?
Yeah, we take out the red ball and we put it back in. You understand that?
Okay.
Yeah. All right, so that means that is going to be equal to, what is 4 times 4? Go ahead, Deja. I mean, Jasmine.
16.
16. 16, 1, 6. What is 10 times 10?
100.
100. So the probability that both balls are red is going to be equal to 16 over 100. Okay, now we could simplify that into, well, we could divide top and bottom by 4, isn't it? And so if we divide this one by 4 and divide this one by 4, we get we get 4 over 25. Okay. So the probability that both balls are red is 4 out of 25. Any questions on that? So quick review. The probability that both balls are red is equal to the probability that the first ball is red multiplied by the probability that the second ball is red. And so we multiply that. The probability of A times the probability of B is 4 over 10 times 4 over 10, which equals to 16 over 100, which equals to 4 over 25. Okay. Now, if we were to do it your way, Deja, with the sample space, let me just.
I know you said it would take forever.
I realized that it's not 100. I thought it was gonna be 100 because this denominator is 100, but I don't think it's gonna be 100 because I forgot that we could reduce it. So let's try to do the sample space way. If we try to do that, okay, here's a mini sample space for you to just to consider, right? So so there are 6 red balls. There are 4 red balls. So if there are 4 ways to do that, that means that okay, order matters. Okay, got it, I got it. So order matters in this case, so that's why it's so much. So look, if you look at it, right? So we have red R1, R2, R3, and R4. And it's gonna be, for the blue, it's gonna be, like if we were to do it for everyone else, you don't have to worry about this. This is just on a side note. Like if we were to do it the long way, and that's why this rule is so important for us, because it gives us a shortcut. So B1, B2, B3, B4, B5, B6. All right, good. So in order for us to figure out all the elements in the sample space, we'll say what? We'll do everything with R1. So it'll be R1 with B1. Sorry, I'm just gonna do it one time. I'm not. Then it could be R1 with B2. Then it's gonna be R1 with B3. You understand what I'm saying, Deja? And it's gonna all the way down to R1 with, until we reach to R4. Good. And then we do the same thing for R2. It's going to be R2 with B1, R2 with B2. You understand what I'm saying, Deja?
I don't really get it, honestly, but
You don't
okay.
get it?
No, I don't get it. Like I understood the dominoes one, not the dominoes, the one with the dice, but I really don't get what's going on here.
Okay, so R1 means that the first ball you got was red. B1 means that the first ball you got was blue. R1 here means that the first ball you got was red again, but the second ball you got here was blue. But blue in the sense that, well, I don't think we need to label them because they didn't tell us that each ball was distinguishable. Anyway, I'm not gonna focus on the sample space now, but just do it this way. We can leave that for another discussion.
That seems like a headache.
Yeah, because then I think the issue is that I don't think I have to label them because at least I'm not sure I have to label them. But anyway, the answer is 4/25. Yeah, forget that. Let's just keep it like this. This way is simpler. So all you need to do is remember that in order to get the first red ball, it's gonna be 4 red balls in total divided by 10 because it's 10 balls in total. Then the second time, remember we replace that red ball back. So it's going to be 4 red balls still over 10. 4 times 4 is 16 and 10 times 10 is 100. And 16 divided by 4 is 4 and 100 divided by 100 divided by 4 is 25. So that's how we get 4/25. Now that is the first question. That's the probability that both balls are red. Now what if I want the probability that both balls are blue? Okay, so I want the probability, this is what, on 48, so I want the probability that both balls are blue. Okay, so if I want the probability that both balls are blue, what must I do, Sienna? I mean, not Sienna, because Sienna can't hear me. Yeah, Sienna should be on the phone, right? Yeah. Sienna, what should I do if I want the probability that both balls are blue?
The first ball is blue.
Okay, so I must, when you say the first ball, you mean I must find that probability?
Yes.
Okay, and then what else? The probability that the first ball is blue.
Times the second ball is red.
Why the second ball is red? Remember, we want both balls to be blue.
I mean blue.
Okay, very good. Times the probability that the second ball is blue. Good, so, alright, so what's the probability that, this one is for Jasmine, what's the probability that the first ball is blue? Jasmine, are you here? Alright, I guess we could try Albernique. What's the probability that the first ball is blue?
6
Albernique.
out of 10.
6 out of 10. Why 6 out of 10?
Because the blue balls are the 6 blue balls. Added together, it would be 10. All because you have six blue balls and four red balls, and you take out the blue ball and you put back in the blue ball. So yeah.
So it's 6 out of 10 because we have 6 blue balls. Very good. And Miss Neely, F. Neely, what's the probability that the second ball is blue?
It's the same thing, right? 6/10, right?
6 over 10. Very
6
good.
over 10. Very good.
6 out of 10. Okay. All right, excellent. So, um, next up, Miss Johnson, are you there? Miss Johnson, are you there? Hello, Miss Johnson, are you there? Okay, I can't hear from us, so Jada,
36.
very good. 6 times 6 is 36. Thank you. Jada Wallace, what is 10 times 10?
100.
100. Very good. All right, good.
6/25.
6 over 25. Very good, Jasmine. So if we simplify it, we can use um, 4 over 10. Sorry, 4 over uh, 25, yes. And the reason, why, no, not 4. Why that sound weird? 9 over
I was just
25.
gonna say,
Yeah, because if we divide top and bottom by 4, 36 divided by 4 is 9, and 100 divided by 4 is 25, so it's 9 over 25. Okay, so what now we're looking for, what's the probability? So this is a question. This was A, both balls are red. B, both balls are blue. Now we want C. The probability that is 48. So C is the probability that both balls are a different color. So we already looked at the probability if both are blue and both are red. But what if we want the probability that both balls are a different color? All right. And that one is interesting because there's two ways that could happen. So if we want both are red, if we want both balls are different color. So if we look at it, it could be the probability of, so we want a probability that both balls are different, or let's say balls are different. So we want both balls different color. I don't know the right whole thing. So with this one, it's slightly different. So if both balls are different color, that means that the first thing that could happen is that the first one could be red and the second one could be blue, right? That could happen. Or, right, or, so you could see that, or the first one could be red, the first one could be blue, or the second one could be red, okay? And remember, when we're dealing with or, we have to add, because or, when we say both balls are different, that means one could be the first one red, the first one blue, or the first one blue, or the first one blue and the second one red. And this is very important. This is an important distinction right now. Here we're looking for both balls having a different color. Remember, there's two ways that could actually happen. So it's two options. All right. Every time you have two options, you're dealing with or. Right. So the first one could be red, blue. So that means the first one you take is red, the second one you take is blue. Or the first one you take is blue, and the second one you take is red. Okay. Now, this one we gotta be careful. So this is actually a very important question. We shouldn't run past by this in any effect. So what's actually happening here is we have the multiplication rule and addition rule combined. So when we say both balls are different color, like I said, the first way that can happen is if you get the first one is red and the second one is blue. The first one is blue and the second one is red. And so my question is, how can we get the first one red and the second one is blue? For that one, we know that we have to use the multiplication rule. The reason why we have to use the multiplication rule is because we have an and. An and means that we are going to use the multiplication rule. So what's the probability that the first one we get is red? Caitlin, what's the probability that the first one you get is red?
4/10.
4/10. What's the probability that the second one we get is blue? Caitlin.
6/10.
6/10. Very good. Notice how we multiply these two, because remember, this is the probability of red and blue. Good. Now, plus, open bracket, we're going to look at the probability of blue and red. So what's the probability of getting blue Sierra the first time?
6/10.
6/10. What's the probability of getting a red the second time? Jasmine.
4.
4/10. Very good.
10.
Good. So let's perform the computations here. Deja, what do we get for the first one?
24/100.
I could barely hear you.
24/100.
24/100, because 6 times 4 is 24, and 10 times 10 is 100. Good. right? Plus, what do we get for the second one? Albernic. What do we get for the second one?
24/100.
24 over 100. Altonic, are you here? Altonic. Altonic, are you here? Albernic, where's your sister?
I don't know. She's supposed to be in another room. I don't know.
Okay.
That's his second.
Yes. Altonic, are you there?
Yes, sir.
Okay, good.
It's supposed to be a multiplication sign.
Why you say multiplication sign?
I mean for the
Green here? There's supposed to be multiplication sign?
no
Yeah.
red thing, red and blue plus blue and red.
Oh, there's supposed to be multiplication sign? Are you saying right now?
Yeah.
Oh no, it's supposed to be addition.
No?
No. Remember I said that this one for this question. This is the question where both of them are different. Okay?
Oh,
Yeah, so remember now, if both of them are the same, right? If both of them are the same, then we could use the multiplication rule and say, okay, the first ball is blue and the second ball is blue, right?
okay.
But for this one, we have both balls are different, and so what that means is that could happen two ways. Since it could happen two ways, that means we have two options. The first one is red, the second one is blue, or the first one is blue, the second one is red. And so remember I had the or here. So it could happen as the first one is red and the second one is blue, or the first one is blue, the second one is red. So since it's the or thing that we're dealing with, we know that we'll be dealing with the addition rule. So we have to use a plus. We can't multiply them. It'll be wrong. So okay, so what is 24 plus 24? That'll give us what? Miss Johnson, are you here?
Yes, sir.
Okay, what is 24 plus 24?
48.
Okay, great. 48. And remember, for when we're adding fractions that have the same denominator, do we add the denominators?
No, sir.
No. So you just leave it as 100. So the answer is 48 over 100, which we can simplify to what?
Over 25.
Say it again.
I got 12 over 25.
12 over 25, yes. Because,
I don't really understand this though.
why?
I don't understand. First, you told us that you'd have to, because this is independent, it's an independent event, you'd have to multiply. But now I see you multiplied and add, and you're using both. So how would I know when to use this?
Okay, it's clear, because look at what you're doing. You want to find the probability that both balls are different, right? Right?
Yes, true.
Good. How much ways that could happen that both balls are different?
You can get a blue ball first and a red ball second, or a red ball first and a blue ball second.
Very good. So it could happen in two ways, right? So you could get a red first, right? And you can get a blue second. This right here is which rule?
Multiplication, but
Right?
go on.
Right? Or no?
I know this is the multiplication rule.
Good. So now let's go to another option that you're telling me. What's another way you can get that both balls are different?
The first one could be blue and the second one be red.
Very good. So the first one could be blue and the second one could be red. Which rule is this?
That's also multiplication.
Very good. That's multiplication rule. Good. So we already get that sorted out. So we know that we have 24 over 100 and 24 over 100. That's what we have, right? So when we look at these two events, right, we have, can these two, okay, this is what you must you ask. Can these two things happen at the same time?
I mean, we have two hands, so I guess so.
They could happen at the same time. So you could get a red.
Are we using our hand? Is this like is it like it's in a container and you using your hands to take out the colors, see which color you get?
Okay, what I mean is, can you both get, the first one is red, the second one is blue, and the first one is blue and the second one is red at the same time? Can that happen?
No, sir.
No. So that means that these events are mutually exclusive, right?
Yes, sir.
Good. So what happened? What do we do for mutually exclusive events?
We're supposed to add.
Exactly. Because it's two options, right? So it's whenever you have two options, so this is way 1 and this is way 2. Once you have two options, you have to add the probabilities. You wouldn't multiply them. Okay? So that's why we add here.
I don't know. Maybe I'm just not getting it.
I don't understand, but
Oh, so like when we have like two things to add, like we have like one by itself, like 6 over 10 times 6 over 10, that's when we have to multiply.
that's when you have to multiply. So with this one, this could happen at the same time. Like, this could happen in one outcome, right? You could get a blue ball and you could get a red ball. So you get a blue ball and then you could get a blue ball. That could happen in one outcome, right? You get put your hand out, get a blue one, take your hand out, get a blue one. These are independent events because the probability of one does not affect the probability of the other, right? Now, when you're looking at these two, these are mutually exclusive. They could never happen at the same time. There's no way you could get red and blue and red in one outcome. It's impossible. So they're mutually exclusive. You cannot multiply mutually exclusive events. You have to add them. Okay? So this is very important. All right. So make sure you wrap your head around this one, Deja, because that is what the tree is about. And that's the
That explains why I can't get the tree. Like not getting this.
Exactly. That's this right there. So you have to know when to combine them. And it's pretty easy. Once you know that OR deals with options, right? And here we have two options. We either could get red, blue, or we could get blue, red. We can't say we could get red, blue, and blue, red. Like, you can't, right? It's impossible. You could get red, blue, or you could get blue, red. Okay, you understand that differentiation right there? You could get red, blue, or you could get blue, red. You can't get red, blue, and blue, red. It's impossible. Okay, so we have to add them, right? Because they're different and because they're mutually exclusive. Okay, hopefully that clears up something for you. Maybe you can think about it some more, but that's that for that. So this is gonna be what do we divide 48 and 100 by? What could we use? We could use 4. So 48 divided by 4 is 48 divided by 4 is 12, and 100 divided by 4 is 25. So the answer is 12 over 25. Okay, so if we have two different balls, if you're trying to find where the balls are a different color, then definitely we'd do it like this. All right, so this is, now we're doing probability, right? When you're getting lost at everything, yeah, we're doing probability now. Okay, so the last part of this question is the we want the probability that both are red if the first ball is not replaced. Okay, so this one is tricky. So we want a probability that both are red, but the first ball is not replaced. So there's going to be probability that both are red, and that's going to be equal to the probability that the first one is red times the probability that the second ball is red. All right, Miss Johnson, are you there? Hello, Miss Johnson, are you there? Okay, let me ask Jasmine, what's the probability of the first ball being red? Jasmine says, oh, Miss Johnson says her mic isn't working. Okay, Sierra, what's the probability of the first ball being red?
4 out of 10.
4 over 10, very good. Deja, what's the probability that the second ball is red?
4 over 10.
Pardon?
4 over 10?
No, that's not right.
You said this first ball is red. The second ball is red.
Yeah,
Isn't it probably red 4 over 10?
the probability that the second ball is red. What is that?
That's why I said 4 over 10.
No, that's not right.
3 over 10.
Exactly. Thank you, Jasmine.
Okay, now I'm not getting
3
it.
over 10. 3 over 10.
How we get 3?
How get you the credit?
You have to read the question. It says if the
I
first
get lost until I see replace.
if the first ball is not replaced. Remember? Look at it. Remember your experiment. Remember your experiment, right? Your experiment is that you have a basket that is full of balls. Okay. So we have 1, 2, 3, 4 balls, and then 1, 2, 3, 4, 5, and 6 balls, right? So if we look at this carefully, they said that the first ball, we can't replace the first ball. So when we take out the first ball, right, that goes away. All right, so that ain't coming back because we ain't replacing it back. We ain't putting it back then. So now when it's time to get the second ball, how much balls we have left to choose from?
3.
3. So it's 1, 2, and 3. Because it's no replacement. You can't replace it, right, in this one. So then it's going to be 3 over 10. But the ones that we are doing before this, like when we did it above, they said both balls are red, but they told us in the question you could replace it. So you could put the first ball back, so that it would have been 4 over 10 again. But in this one, we can't replace the first ball, so we have to leave it outside. All right, so it's 3 over 10. Okay, do you all understand it, or should I explain it again?
I understand.
Okay. See how you get it? Say it again.
Can you explain it again?
A little. Okay. All right, no problem, Caitlin. So the idea here is that in this one we have 1, 2, 3, and 4 red balls. Now they want the probability that both balls are red. So we have to take out our first red ball, and for the first red ball, we have 4 outcomes that we could choose from. This one, this one, this one, or this one. So it's 4 of these we could choose from. So that's why it's going to be 4 out of 10, because it's 10 balls out in total. Now when we reach to the second red ball, remember, we already took out the first red ball, and we are not replacing it back. So for the second red ball, we only have 1, 2, 3 red balls to choose from this time. So that's why it's going to be 3 out of 10. Okay, for this. You understand, Sierra?
Yes, sir.
How about you, Caitlin? You need me to explain it again?
I understand it.
Okay. So we have to account for not replacing that red ball. Okay, so be careful of that. Clear all drawings. Alright, so simplify that for me and let me know what you get. Alright, so what was the answer? Final answer. For the probability that both are red is what? Anyone?
3 over 25.
4 times 3,
And 12.
12. 10 times 10 is
10 times 10 is 100.
100. Very good.
I can't hear nothing.
Okay, so it's gonna be 4. Sorry about that. It's gonna be 4 times 3, which is 12. 12 over 100. Let me simplify that. What we get, Deja?
3 over 25.
3 over 25. Yeah. So we have to be careful, especially with these questions. Be very, very careful. Okay, so let's go to our problem sets, right? So, yeah. So let's look at this problem set. So let's look at this exercise. Exercise number 1. Okay. So it says a box contains a box contains 6 red socks and 4 white socks. A sock is taken out at random and put back in the box. A second sock is then taken out. What is the probability that A, both socks are red, B, both socks are white, C, both socks are a different color, D, both are white if the first is not replaced, both are different colors if the first is not replaced. Alright, so those are our questions for exercise 1. I'm going to give you, how much time do y'all need for this? 2 minutes?
3.
3 minutes.
3? Okay, 3. Alright, so 3.
Excuse,
Go ahead. The time has begun.
excuse me, Mr. Isaac.
Go ahead.
We have to write the probability, we have to write the probability and all that stuff, or we just have to start off with the numbers.
Right, the probability that both socks are red, just like how I have it in brackets. Okay? Alright, that's time.
I only finished one.
Alright, let's start off with the one you finished then.
Same.
Probability that both socks are red. Jasmine.
I can do it.
Go ahead.
I event A, and I put
Mm-hmm.
the first box is red, then event B, second box is red.
Mm-hmm.
Then I do P equals first box is red times second box is red.
Mm-hmm.
I get 6/10 is 36/100.
Okay. Okay.
I simplify it to 9/25.
Very good. So if we want the probability that both socks are red, we're gonna say the probability both socks are red. That's gonna be equal to the probability that the first sock is red. Remember here we were replacing it. So we taking it out the box and putting it back. And so that means we're gonna have the 6/10 because it's 6 red socks and 10, sorry, 6 red socks and 10 overall, times 6/10 because it's 6 red socks. Still, because we put that first red sock that we took out back again, we put it back in. And so it's going to give us 36/100, like Jasmine said. Once we simplify it, it's going to be equal to 9/25. Alright, C. Alright, can y'all hear me? Sienna, are you here? Sienna, are you here?
Yes.
Okay. Help me to do B. What's the probability that both socks are white?
4/10
Okay, 4/10. That's it?
times 4/10.
Times 4/10. Okay. And what's the result gonna be?
16/100.
16/100. And if you simplify it, it'll be what?
Four over 25.
Very good. 4/25. Okay, probability that both socks are a different color. Go ahead, Deja.
Sorry, I'm not even on that. I'm not even on that yet. I'm not gonna lie.
Oh, so you want E?
I'm still working. I'm not even on that. I just finished B.
You just finished B? Okay, so let's do C together then.
I just finished B2.
I almost done with B.
Can I do C?
Okay, go ahead, Caitlin.
Well, this is Taisha.
Oh, Taisha, what happened? And you say your mic wasn't working?
It wasn't working, but I had to log out and come back in.
Oh, okay, okay. All right, let's go then. How do we do C?
Would it be 6/10 times 4/10?
6/10 times 4/10. Okay. That is very good because 6/10 is going to be that we get what? A red, right? And then
That's right.
4/10 is going to be that we get a blue, right? Not a blue, a white. Okay, that's good, but it's not complete. There's another way that could happen. What if we get a white first, then a red? Okay,
It'll just be the opposite.
very
4
good,
times 10. 4 over 10 times.
very good. 4 over 10 times 6 over 10. Very good. That's gonna be equal to I ran out of space. It's gonna be equal to 24 over 100 plus 24 over 100. So it's gonna be
48.
48
Okay.
over
Over
100.
200.
200? Remember, we don't add.
Oh, sorry.
Yeah,
100.
yeah. Okay. 48 divided by 100. How can we simplify that?
12 over 25.
Yes, 12 over 25. Very good. Okay, good. Okay, Deja, help me out with D then.
Okay, I just came on this, but that would be 4 over 10 times 3 over 10.
So we want both white if the first is not replaced. Very good. So it's gonna be okay. Let me just write the answer because it's just taking too much space. 4 over 10. That's for the first one that is white. Times 3 over 10. That's for the second one that is white. It's gonna be 12 over 100.
And simplified, we have 3 over 25.
3 over 25. Very good. Both colors are different if the first one is not replaced. Why did they do this to us? Alright, so this one is going to be a little bit different. So you have to think with me. We want both colors are different. So there are two ways this could happen. So the probability both are different could happen with us having so probability both different. Remember, there's no replacement though. So this could happen in two ways. The first way it could happen is if we have first a red sock, then a white sock. So what's going to be the probability of getting a red sock, Albernique, at first?
Repeat what you said, please.
The probability of getting a red sock. Hello, Albanic, are you there? What's the probability of getting a red sock?
Okay, so there would be like 6 over 10.
6 over 10, very good. Now, what's the probability of getting a white sock?
At 4 over 10.
4 over 10? 4 over 10?
Yes, sir, 4 over 10.
Okay, that's not correct. Anyone else want to help her?
Six over 10.
No, that's not correct.
5 over 10.
No.
3 over 10?
Nope.
12 over 10.
Nope.
4 over 10.
Nope.
Is this 6 over 10?
Nope. Anyone else want to help her?
Five over 10? 5 over 10?
No.
Is it 9 over 10?
No.
Another.
Sierra, help them out. Save the day.
0.
6. uh,
I don't understand it though.
No.
1
Deja, save the day. Save the day, Deja.
Oh boy, I'm just as clueless as everyone else.
I think it's 10 out of 10.
10 out of 10. Mercy. You know what, Kate?
I said that.
Caitlin, save the day. Save the day, Caitlin. Save the
I
day.
don't know. I don't know.
All right, Miss Johnson, save the day.
Is it 10 over 10?
No.
Okay. 6 out of 10.
No.
4 out of 10?
3 out of 10.
No.
0 out of 10.
No.
2?
No.
4 out of 2?
All right. No. All right, think about it. Remember, the first one we got was red. That was the first sock, right? When we get that red socks out of the box, right? Do we replace it in this question for E? Do we replace it?
Yeah.
No.
Yeah.
No, we do not replace it. Say the first is not replaced, right? Good. So how much socks we have in total now for the second option? How much socks we have in total?
10.
You can't still have 10. Remember the first is not replaced, so that we already take that out. So how much socks you have left inside the
9.
you have
9.
9, exactly. You have
So
9.
it's 4 to 9.
Exactly, it's 4 to 9. Okay. So be careful.
I don't.
Alright. Remember, let's look back at our box. We had 6 red. 1, 2, 3, 4, 5, 6, and 4 white. I can't use white because you wouldn't see white, but I'm gonna use blue. 1, 2, 3, and 4. Good. Remember, for 6 out of 10, you already took out that red one. So 6 over 10 is for the red. So we already took out the red, one of the red. Okay? So we already take that out. That's gone. Right? Now it's time for us to take out a second sock. How much we have to choose from? 1, 2, 3, 4, 5, 6, 7, 8, 9. We only have 9 to choose from. Now how much of them are white? 4 are white. So it's going to be 4 over 9. Okay? Do we understand that, or should I explain that again?
So I understand it a little teeny bit.
A little teeny bit. Remember, you took out the red one already. So you only have 9 left. So it's going to be 4 over 9. 4.
How on earth did we get 9? That's the question.
It was 10 socks. You take out 1. Now you have 9.
Okay, so why that one is an 8 then, since we're taking out another sock?
No. Very good question. Remember the definition of probability. The number of elements inside your event divided by the number of elements in the sample space. So how much options you have? How much white socks do you have? You have 4 white socks. You ain't take out the white socks yet. How much white socks you have to choose from? 4. How much out in the entire box? 9. So it's 4 to 9.
Wait, are you saying that? Are you saying? Hold on. You're saying that okay. So it's what? You're saying okay. So it's 4 to 9 because when we did the Red Sox, because we took out a red sock, we're left with 9 because that sock is gone. We didn't put it back.
Yes.
So that's how come the denominator for the white sock is 9, right?
Yes.
So how come it doesn't change for the next one we're doing? I don't get it. How come that's not 8? Aren't we still taking out a sock? I don't get it.
Okay, very good. Okay. So remember, look at, you mean for the first one, how come the first one is not 9? That's what you're trying to say.
No, I mean, how come this one be going on now? Where your first sock could end up white. How come that denominator is not 8? Because are we taking out a sock? So if we take, okay, so we started with 10, but we take out the sock, so we end up with 9. So we taking out another white sock, so that denominator should be 8, right?
No.
I don't get it.
No. Okay, look at your first probability, 6 over 10. Explain 6 over 10 to me.
Well, 6 represents the amount of red socks, and 10 represents the socks you have altogether.
Very good. That's exactly what we did for the second one. We have 4 white socks and 9 options to choose from.
Because we took the red sock out.
Because we took the red sock out.
Exactly, that's what I'm saying. So when we went on, you were saying that the other, okay, we're going on to white and red, right? You were saying that that's gonna be 4 over 9 too. I don't get it.
Oh,
why isn't it 4 over 8?
Okay, good. So 4 over 9. You mean for the white and red?
Yes, sir.
Okay, we didn't do that yet. Let's do it now. So the white, now remember, this is OR. These two can't happen together. They can't happen at the same time. And they can't happen one after the other. And they're not happening one after the other. This is OR. One could happen or the other one could happen. So this one is not connected to this one. Remember, they're mutually exclusive. They can't happen at the same time. So when we doing now, we got to choose a white one. Then we're going to choose a red one. So what's the probability of choosing a white one, Sierra?
4 to 10.
4 to 10. Very good. Now, Deja, what's the probability of choosing a red one? Go ahead, Deja. What's the probability of choosing a red one?
I'm just. Are you? Will it be 6 over 9?
Yeah, of course, 6 over 9.
This is very.
Yeah. What's so hard about this?
So you're saying that these two events happening here, they're not happening at the same time.
No,
so
they're mutually
what's
exclusive.
going on in this first bracket would not be going on in the second bracket. So
No.
you have to start over again.
Yeah.
Wow.
Okay. So what is 6 times 4? That's what? Jasmine, what is 6 times 4? Where's Jasmine? Jasmine is there? No. Sierra, do you understand? Or you still need some more explanation?
That needs more explanation.
Okay, on what part?
Um, the whole thing, I guess.
I was hoping you didn't. I was hoping you didn't say that. I was hoping you didn't say the whole thing.
I'm very lost. I guess in these answers.
Mm. Okay. Do you understand what we when for both socks are red? You understand how we got that? For
Yes,
both
sir.
socks are red. That one is easy, right? I assume
Uh-huh. So,
because 6/10 times 6/10 because we have 6 socks that are red and 10 in total, and then we can do it again. 6 are red and 10 in total, right? Do you understand both socks are white? Explain this to me. Why we have 4/10 times
yeah.
4/10?
Because
Explain.
both socks are white.
Okay. And because we replace what? When we took out
The
the first,
red socks, the white socks.
yeah, when we took out the first white sock for this one, right? We put it back again. So that's why this denominator is still 10. And that's why this is still
Okay.
4. Because when we took it out, we put it back again. You understand that or no?
Yes, sir.
Okay. All right. Now, I guess it's C where things start to shake up. So probability of but both colors are different. Um, explain this portion to me. Why we have 6/10 times 4/10?
Okay, so you have two different color socks,
Mm-hmm.
and like either white or red could come first.
Mm-hmm. Mm-hmm. Very good. So if red come first, what would be a probability?
Red, it'll be 6/10.
Good. Then after that, you're trying to get a white one. What will be a probability?
4/10.
Good. That's one option. And then what's the other way gonna happen?
Or red or white come out first, which would be 4/10, and then red will come out after, which would be 6/10.
Good. Very good. All right. And the reason why it's all these denominators are 10 is because remember we every time we put it back. So when we take out that red sock, we put it back. So it's still gonna be 10 red, 10 socks in all for us to choose from. All right. That's why the denominators do not change for these 3. All right, because these are with replacement, with replacement, with replacement. Now let's go to D and E. So let's look at D. So let's say both are white if the first is not replaced. Explain this one for me.
Okay. So, okay. So I have no idea.
Okay. So the first time it's gonna be 4/10, right? So that's the white one. Okay, so 4/10, that's the white socks, right? Because it's only 4 white socks and it's 10 in total, right? Multiplied by, remember, we are going to take out a white socks and we're not going to replace it back. All right, so D is actually wrong, you know. It's supposed to be, please change D. It's supposed to be, when you look at it, we're not replacing back this white. So when we take it out of the box, we're going to have 9 socks in total. So it's going to be 3/9. All right, so both are white if the first is not replaced. Both are white if the first is not replaced. So the first time we take out this box is going to be 4/10. multiplied by 3 over 9 because, okay, look, think about it. It's easy to visualize, look. So, like, we could literally do the experiment here. So, there are how much white? 1, 2, 3, and 4. How much red we have? There are 1, 2, 3, 4, 5, 6 red. Okay, so remember, we're going to take out a white. All right, so let's take out this white. We're not going to replace it. So that means that we had 4 to choose from out of this 10 for the first one. So 4 out of 10. Now, when we go back to take out the next white, we only have 3 whites to choose from, right? And remember, we do not replace the same white, so it's going to be 9 in total. So it's 3 whites and 6 reds. It's going to be 3 over 9, which is going to be equal to 4 times 3 is 12, and 10 times 9 is 90. So divide top and bottom by, we could divide by 3. Yeah, the best bet is divide by 3. So 12 divided by 3 is going to be 4. It's going to be 4 over 90 divided by 3 is 30. Okay, so if you understand D, you could understand E. So let me explain D again. Again, for D, remember, we're trying to get the first one to be white. So remember, it was 4 whites in total and 10 socks overall. So we remove 1 sock because we already take that white sock out. Now, how much socks are we left with? How much white socks we left with? Just 3. So it's going to be 3 white socks and 9 socks in general. Okay, that's why it's 4 over 10 times 3 over 9. So does that make sense to you, the 4 over 10 times 3 over 9, Sierra, or I should explain it again?
Yes, sir. I got it.
All right, good. Now, Deja, does that make sense to you or no? I need to explain that again.
No, I understood D.
Okay. Now, let's go to both are different. Now, if both are different, there are 2 ways this could happen. You could have a red socks and a white socks, or you could have a white socks and a red socks.
Wait,
Okay.
no, I just realized I had the wrong thing in my book for D. No, I don't get it. Oh no, I get it. You take out. Wait, you're saying that when you did white first, the white sock that you took out wasn't put back, so that's how come the denominator get 9. I understand it.
3 over 9. Okay, good. So the same thing applies.
Wait a minute. Hold on. How we get 3 on top then?
Okay. How much white socks you have to choose from?
4.
4? How 4? You already took out 1.
Wait, no. Huh?
You already took out 1. You understand that?
Okay. Okay, I understand that. I understand.
Yeah. And how much socks you have in general left over?
9.
9. So it's 3 over 9. Okay. Now, for this one, we want both socks are different. So, and we do not replace. That's the difference. That's the thing right there. We do not replace. So it either be red and white or white and red. Okay. So if we doing red and white, the first one is going to be red. That's going to be 6 over 10 times 4 over 9. Sierra, can you explain how we got this one? Explain that for me. Let me see if you understand.
Okay, so the 6 over 10, it's because, okay, you have 2 different color socks, which is red and white, and the red has 6 and the white has 4, which in totals give you 10. So for the red, Hold on. Okay, so for red, it's wait, what? Red. Okay, you have two different colors,
Mm-hmm.
red and white.
Mm-hmm.
Mhm.
Why do we have the 6/10? Why do we have 6/10, Sierra?
I don't know.
What? You don't know? Okay, think about it.
I have no idea.
Okay,
Okay, so how if
one
the
moment.
first is not replaced? So okay, how you have 4/9, but you didn't change the 6/10 if they the same? I don't know.
Okay, so 6/10, wouldn't that be 4? So 6/10, how much red socks do we have in general?
I don't know.
How much red socks we have? Don't we have 6 red socks? Or no? Sierra, you have? I know it's a little difficult, but think through it. How much red socks we have? Sierra. Alright, hello? Can you hear me?
That's all.
Okay. How much red socks we have, Sierra?
6,
6. Good. How much socks we have in total?
10.
Good. So that's why we have the 6/10. Is that clear?
That's all.
Good. Now, remember, we do not replace that we don't put that red socks back. So how much socks we have in total left over?
9,
9. Very good. How much white socks we have?
4.
4. That's where we get the 4/9. So is this clear?
Okay, that's all I get it.
Okay, now explain this side.
Okay, so there are 4 white socks,
Mm-hmm.
and in total we have 10 socks.
Mm-hmm.
And then with the 6/9, we have 6 socks, and okay, and out of the 10 socks, one would be missing, so that's how you get 9.
Mm-hmm. That one missing was what color?
White,
White. Very good. Excellent. So what is 6 times 4? That's what?
24.
24. Deja, do you get it? Or are you still struggling?
Yes, I don't get.
I understand.
Okay.
I don't get.
Go ahead. Go ahead, Albanique.
I don't. How come there's like a 3/9?
How how for this one we get 3/9?
Yes, not 3/10.
Very good, because remember, look, if we look at our box, this is 1, 2, 3, 4, 5, 6, and if we look at our white, it's gonna be 1, 2, 3, and 4. So Albanique, how much white socks we have inside this box?
4.
4. Good. So it's gonna be 4/10. for the first white box, white sock, right?
Yes, sir.
Okay, now we're gonna take out that white socks, right? And we're not gonna put it back. So we take it out, and so this is here and this is there, no more. We don't have no more of this one. So my question to you is, how much white socks we have inside this bag?
3,
3, very good. Now how much socks we have in total in the bag?
9.
9, very good. Okay. All right, so 6 times 4 is 24. So you understand how we get the 3/9, Albanique?
Yes, sir.
Okay. All right, 10 times 9 is 90 plus 4 times 6 is 24 over 90. So we have, what is 24 plus 24? 48 over 90. And this is going to be equal to, what is 48 divided by 90?
I got 8/15.
8 over 15. Eight over 15. All right, excellent. 8 over 15. All right. Any questions for me? All right, so I know this one is a bit challenging, but yeah, we got through. Deja, you're the one who said you wanted to do tree, right? So this is the beginning of the tree. Is once you get this,
I'm getting a headache, but I shall persevere.
yeah, this multiplication rule. Multiplication rule is always interesting because trust me, you're not the only one. Even some math teachers who teach and they hate probability with a passion, you know. And so, but I like probability. Probability. At first, I didn't like it until I did this math course at the university. This was Math 360, and the whole course was just about probability. And I began to understand more and more, like what probability is, and I mean, once you understand it, then you begin to like it because you find that you're getting the questions right. So, yeah, this is probability at heart. So hopefully, we can do some more questions like this, and we can. So we definitely got to continue doing these questions, so that we can get more use or accustomed to doing questions like these, so that it wouldn't be a so it wouldn't be something that is overwhelming because you're getting accustomed to doing it. All right, so right about now we're gonna transition over to English. All right, so let's do that. We don't have a lot of math notes today because explaining this took a lot of time, but sometimes it's like that. So sometimes it's like that. All right. Okay.
Yes, ma'am.
All right. So let's save this. This is going to be multiplication rule for probability. All right. Let's move on to English. The last thing we were doing in English was joining things together, sentence combining. All right. And so we're going to continue along that same path. Okay, so we was looking at we was looking at sentence combining using using the subordinating conjunctions. All right. We didn't do a lot. We just did what, three examples of combining sentences using subordinating conjunctions. So now we're going to continue on our journey of combining sentences. Anyone can remember why we said that it's important to combine sentences in the first place? Anyone can remember why we said it's important to combine sentences in the first place?
So it can make a complete sentence.
So they can make a complete sentence. Okay, that's an option. But remember, the sentence is already complete. So why we need to, like for example, we rode the merry-go-round and we rode the Ferris wheel. They are two sentences. Like they're not improper sentences. So why would we want to combine them in the first place?
That's what I really didn't, when I was doing this, I really didn't get that because like they two independent class, like they don't even need,
They don't need the combination. So why would we combine them? Yeah, got you there. I told you all why at the beginning of when we did the introduction to sentence combining. If you still have your notes, you can look at that. But what I said was, I said that, remember when we reading little children books, they have sentences that are very simple. So I went to school. I loved James. The cat is nice. The rainbow is beautiful. Like those are sentences that are very short. All right. Now, for more mature writers, we need to have sentence variation in the sense that we need to have varying sentence lengths. Okay. So we were frightened. That is a simple sentence and it's very short. But if we want to increase the length of a sentence, we can combine two sentences into one. So instead of saying we were frightened, the ride went so fast, we can say we were frightened because the ride went so fast. What that does for us is that increased the length of the sentence. All right. So if you want to have different variation in sentence length, that's one of the reasons why we combine sentences. Another reason why we combine sentences is because if they have the same idea, right? If the two sentences share the same idea, we don't want to, typically we want to combine them because they're saying the same thing or they're saying something that's very similar, all right? So you could say for example, I said John went to the bathroom, and my next sentence is John went to school. Well, I could say John went to the bathroom and to school, right? So I combine it into one sentence, right? So that is something. So we combine sentences to have varying sentence lengths, right? And we also combine sentences to, excuse me, to be more um I don't want to use the word concise, but to be more distilled in what we say. So we wanna ensure that we don't distill, yeah. Like when I say distill, I mean we want to get to the point, and we want to keep the truth. We don't want to have anything that is distilled water. Distilled water means something that is free from all impurities. So if you get to the meat of the matter, like without having any extras, that's what I'm trying to say. Okay, so that was the last thing that we was doing, combining sentences using a subordinate subordinate subordinating conjunctions. The next thing we're gonna use is the next way to combine sentences we're gonna use is we're gonna combine sentences by changing one of them into a phrase. Okay. So let's do that. So sentence combining part 4. Today is let's keep it at 48 and let's have this in the back here somewhere. This is Monday, Tuesday, Wednesday, Thursday, Monday. Today is Monday, the 15th of August. And we're looking at sentence combinings, but this time is part 4. So let's begin with the key concept. Let me reduce this. So the key concept for this particular discussion is we want to note that we can combine sentences not only with subordinating conjunctions, not only by using a comma and a coordinating conjunction, not only using semicolons, right? But we can combine sentences by changing one of them into a phrase. So sentences can be combined by changing one of them into a phrase. So when combining sentences in which one of the sentences simply adds detail change one of the sentences into a phrase. So for example, let's say we have this uncombined one. So we have this one, my team plays tomorrow. We play the Tigers. So if we look carefully, this sentence just adds more detail to the first sentence. All right. So what we could do is that we could just say, well, my team plays against the Tigers tomorrow. Also, we could combine them. So we say that my team plays against the Tigers tomorrow. Instead of just having all two of them, we just combine them into one, and it makes sense. It makes your, so here we have two simple sentences, and here we have one that is a little bit more complex. Not totally more complex, but it's a little bit more complex, and plus it shows skill in bringing two things together, two ideas together. Not only you talking about your plays, not only you telling me that your team is playing, not only you telling me when, you telling me who they're playing against. So we have all those dynamics in one sentence. So you're being more concise with your word. You're being more efficient. That's the word. You're being more efficient with how you write. So we can say, so uncombined is so we say my team. So say for example, this uncombined one, my team will play against the Tigers. It is the only undefeated team in the league. So how can we combine this? Well, we can say my team will play against the Tigers, comma, the only undefeated team in the league. All right, so you see how we took two sentences that were about medium-sized sentences, and we combined them into a much longer sentence. What this does to your essay is that if you could have sentences that are longer in length, medium-sized, small, long, medium-sized, small, and you vary them, right, the better your essay would be. So you want to have varying sentence length. So that's what we look for. So not all long or all short, but variation. All right. Now, just not just unwise variation, because some variations are not needed, but wise variations that actually are meaningful. So this making them these two together, it makes sense, because it's like, well, they talking about this sentence talking about the Tigers, So might as well just put them together, right? So then there's that. All right, so let's look at another one. So uncombine, we have
Whenever I try that same thing you did there with combine, I
yeah.
seem to keep knocking me down for comma splice or whatever she called it.
But
What
this
is
is
that?
maybe your sentences are too long in general, and to put them together probably may be too long, right? These two sentences are not extremely long. You know what I'm saying? Like, and they could stand on their own, right? But we could put them together because remember, what we did is we changed them into a phrase. All right, we changed one of them into a phrase. So when we have the undefeated team in the league, right? That, like, if I did say it is the only undefeated team in the league, that wouldn't have been right, say, because I don't need to say it is the only undefeated because we already know what we're talking about. Now, if I want to separate it, then I could separate it, right? Then, of course, I need the period, but a comma here is fine because the only undefeated team in the league is not a sentence, right? The only undefeated team in the league, like that's not even a complete thought. You see what I'm saying? But what you probably have done is you take two things that are complete thoughts and you put them together, and that's a comma splice. All right, so we don't want to do that. You want to frame it in such a way that one of them don't stand on their own. So the first one does stand on its own. That's the independent. It's an independent sentence because it's a my team will play against the Tigers. That's complete. That's a complete thought, right? The only undefeated team in the league doesn't stand on its own. It needs the first one to stand. So we could combine them two together. All right. So that's how you do it. So uncombine. So let's say our class went to the amusement park. Does that answer your question, Deja? Or you need another example or something?
I may answer today.
Okay. Our class went to the amusement park. We went there for the entire day. So how can we combine these two sentences? Our class went to the amusement park. We went there for the entire day. Can we not say for the entire day? Our class went to the amusement park. Okay. Next thing is uncombined. We have the roller coaster thrilled us. The roller coaster has 6 loops. So if we combine these two, What can we say? How can we combine these? Sierra, or you wanna try?
Okay. I don't know how to word it.
You don't know how to roll it? Okay, no problem. Deja, you wanna try?
Uh, the roller coaster thrillers. No. The roller coaster has 6 loops and builders.
Okay,
That sounds weird.
that sounds weird. I mean, that's a combination. Um, you use and it thrilled us, and it thrilled us, and it thrilled. That could work. And it thrilled us. So that's the phrase there. And it thrilled us. But that could work. I was thinking the roller coaster, which has 6 loops, thrilled us. That's what I was thinking. But what you said could work as well. The roller coaster. It just seemed like a weird addition, right? Like the roller coaster thrilled us, and it had 6 loops. And it seemed like a irrelevant detail, but I guess that's what it is. All right, so we could say it like that, or we can say, let me just put another variation just to give you some more. We can say the roller coaster, which has 6 loops. I like this one better because it's describing the roller coaster. Thrill dust. All right. Okay. All right. So before we end, I want to end on a. So this is what we're gonna do before we go. I'm gonna give you a word, and you're gonna tell me what the word mean. All right. So we're gonna end with vocabulary words. So I'm gonna begin with who wants to go first?
Me.
Okay, you wanna go first? Okay. What
I
do?
want to go second.
Okay, that's Sienna or Caitlin?
Caitlin.
Okay, Caitlin. All right. Okay, Altonique. What do we mean by genuine? Genuine.
Nice.
That's close. Genuine. Anyone help her? If someone is genuine, they're what?
When they offer you something,
Okay, that's true.
I know what it means.
Go ahead, Albanique.
When you're being real with someone.
Yes, when someone is real, I like that. If someone is genuine, that means that they are not fake. So they show their real self, and they don't pretend. Okay. All right, Caitlin. Ferocious. Ferocious. What does that mean?
Fierce.
Fierce, yeah. Okay. That's what's the opposite of ferocious?
Gentle.
Gentle, yes. Very good. Okay, Albernique, this one is for you. What I mean by unique? Unique.
When you're special.
Say it again.
When you're special.
Special. That's close, but unique means more than special. What does
When
unique?
you're different.
Anyone want to help her?
When
Unique
you're
means
different from someone.
different from someone else. Okay, that's close too. Unique means one of a kind.
One of a, I guess that's what I said.
Yeah, one of a kind, yeah. All right, who wants to go next? Everybody gotta go, so let's just
I'll
get.
go.
Okay, who said they will go? That's who.
Sienna.
Okay, Sienna. What do I mean by lofty? Lofty.
What's the word?
Lofty. 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 Lofty.
Tall.
Tall. Yeah, that could work. Lofty also means high. Like if you stand on a lofty vantage point, that means that you are very high. Lofty could
Giant,
also, yeah,
imposing.
yeah. Lofty could also mean um impressive in a sense, um, or great or grand, stuff like that. Okay, who's next?
Me.
Jasmine. Okay, your word is chronological. Chronological. When I say chronological, what does that mean?
Um, like in order.
In order. Very good. In order. So if you want something in chronological order, so the first one first, second one second, third and fourth. Chronological. Very good. Okay, who has not gone? Miss Neely. Are you
You
here?
go ahead.
Okay, your word is accumulate. What do I mean by accumulate?
Add up together.
Yeah, add up together. That's correct. Deja, you ready for your word?
Let's go.
Your word is unanimous.
Pardon?
Unanimous.
Everyone.
Everyone.
Or like when I hear unanimous, I think like when the jury makes a unanimous decision, like it includes everyone
Yeah, so everyone voted for that decision.
unanimously, yeah.
Yeah.
Or like when you have elections,
Very good.
like majority rule or something.
Yeah, unanimous. So unanimous means you're in the ballpark. That's fine. All right, Sierra. Since you're the
What's up?
last one, you get the hardest word. I'm just kidding. What do I mean by congruent? Congruent.
I have no idea.
No. You want to pass it on?
What was the word?
Congruent.
Okay.
Congruent?
Yeah, congruent.
Oh, I thought you said conglomerate.
Congruent. 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 Anyone?
You said congruent?
Congruent, yes, congruent.
You mean like harmony or something?
Yes, very good. That's exactly what it means. So, congruent means it's a mathematical term. We could also use it in, and also it's a term we use in maths a lot, and it's also a term that can be used even more than math. So, if something is congruent in math, that essentially means that they are the same in a way. If we say that, see if I can use a congruent in a sentence, or to give you an example that we made. So if I say that Jasmine's ideas was congruent, or Jasmine's behavior was congruent with the the principles of, say, the Constitution. So if I say Jasmine's behavior was congruent with the principles of the Constitution, what I'm saying is that her actions or her behavior was in line with whatever the Constitution say. So that means that she didn't deviate. She followed it perfectly. So congruent basically means that you are in harmony with something, like Albanic said, that you follow it through and through. Okay. All right. If we have two shapes that are congruent, that means that they are, in a sense, equal with each other. All right. So yeah. So like they have the same. So a triangle and a square, they're not congruent, right? Because they don't have the same size and shape. All right. So that's what we mean by congruent. So those are vocabulary words. And hopefully next time we can do it again and deal with some other words that are of importance to us. But that's it for us. Make sure, please send in the class notes. Some people have already begun send them already. That's excellent. And so I'll see you all tomorrow, God's spare, at 6 o'clock. I'm going to be on time. And have a wonderful evening.